So far we've proven the easy direction of the Cauchy criterion. That was that if a sequence converges, then we showed that it must also be Cauchy. And now we're starting with a series of steps that's going to lead us to the more difficult direction, that if a sequence is Cauchy, it must also converge. One of those steps is to first show that all Cauchy sequences are bounded sequences. So we start with the assumption that a sequence is Cauchy, and now we're going to show that it must also be bounded. So to show that, we have to produce a bound. And the way we do that is to use the Cauchy criteria, the Cauchy property with a well-chosen epsilon. So let's let epsilon be 1. It actually could be just about anything, but 1 is easy. So let epsilon be 1. Then since the sequence is Cauchy, there exists a capital N such that if M and N are bigger than capital N, then A sub M minus A sub N is less than 1. All right, the Cauchy criterion says we can arrange for the difference in the terms of the sequence to be as small as we like, so we can certainly make it as small as 1. So this works for any M and N bigger than or equal to capital N. So let's suppose that note that in particular I could actually use capital N as one of my choices. Right? Little n just has to be bigger than or equal to capital N, so let's let it be capital N. Because once we do that, we're going to see how we're going to arrange a bound for the rest of the sequence. Right? By the triangle inequality, or rather the related exercise based on the triangle inequality. So I'll just say roughly, by the triangle inequality, I know that AM minus AN in absolute value is also less than 1, because it's less than AM minus AN without the absolute values inside. So this implies minus 1 is less than AM minus AN. Right, so if we drop the outer absolute values, the thing inside, it has to be stuck between 1 and minus 1. Then we move the A sub n over. And so what we've done is we've produced a bound for every member of the sequence once it's passed capital N. And that bound is 1 plus the absolute value of the A sub n term. So what's missing is the bound for the previous n minus 1 terms in the sequence. Right, so this bound works as long as we're past A sub n. So we need to make sure our bound works for everything before it. So our eventual bound is just going to be the biggest number out of A1, A2, all the way up to A sub n minus 1, and then 1 plus A sub n. So we've got all the members of the sequence up to the capital Nth term, and then we've got this bound that works for everything past the capital Nth term. And so if I take the largest of all of those numbers at once, every member of the sequence has to be smaller. And A sub n is less than capital M for all n. Right? So that should complete that proof. One little detail that turns out it's okay is that in the definition of bounded, capital M has to be strictly bigger than 0. And while it is possible that we have this sort of really uninteresting sequence that starts off with all zeros, notice that the bound here for the rest of the terms can't be 0. It's 1 plus something that's non-negative. So if I take the max of all of these, I definitely am going to get something positive because at least one of them is positive. Right? So that should conclude the proof of that lemma that all Cauchy sequences are bounded.